All right. I think we're ready to get started. Good afternoon. Before I get started, do we have any announcements from anyone? All right. Okay. Couple of quick housekeeping announcements before I get into the topic for today. Number one, next week, Sawmill and West will be presenting. That will be the first student group, and the week after that is going to be Siddhi and Branch, correct? All right. So I know we both just talked about it, but we can set up a meeting to discuss what you guys are going to do as well. So I will try and do some justice to this topic today, quantitative bias analysis. As I was preparing these slides, I realized this is a much larger topic than, I already knew that to some extent, but this is truly a semester-long topic if we needed it to be. And I'm going to try and do justice to this in about 45 to 50 minutes, but that is a really, really tall task. So I will do my best. And if you're running against time, just stop me. And if you have any questions, raise your hand. I'm happy to answer them as best as I can. I will say that most of the content from this presentation comes from a couple of articles along with the textbook that are all listed at the end of this presentation under resources slide, which is all available on Blackboard for you guys to access whenever you want. My goal for today's presentation is to not tell you everything about quantitative bias analysis, but to give you an introduction to what this is, demonstrate how simple it really can be, and then try and motivate you to use these in your thesis projects, dissertation projects, or other projects, and then show you some resources where to go find more information and do your own quantitative bias analysis. Okay. So the outline will be, we'll do an introduction. I'll talk specifically about the types of bias affecting epidemiologic analyses. We will talk about QBA, quantitative bias analysis, only for selection bias today because we are not going to have time for everything else. And then we'll talk about multidimensional QBA, probabilistic QBA, and then some recommendations for implementing it. I am aware that we've got students in the room at all stages of the graduate program, which is more than welcome, but I'm going to start with the introduction so that our first year students, our second year students that may not have been introduced to more epidemiologic association studies can also understand where we are, okay? So let me begin with this. When we conduct an epidemiological study, and this is true in pharmacoepidemiology, or largely in most socio-behavioral research as well, the goal is to find an association between two variables, right? We have an exposure and an outcome. We want to understand if taking the COVID vaccine prevents you from getting hospitalized due to COVID, or we want to understand if taking statins reduces your blood pressure, or whatever else, right? We want to understand the relationship between an exposure and an outcome, and that's the goal of most epidemiologic studies. When we do these studies, we often present the results of our associations in terms of an effect estimate, things such as an odds ratio, a risk ratio, or a parameter estimate, usually from a multivariable regression model of some sort. So you can say, hey, I controlled for several other variables, and then I found that the relationship between this variable of interest and this variable of interest is this much, and therefore so on and so forth. When we do this in pretty much every single epidemiologic paper you read today, or social behavioral research paper you read today, these effect estimates are often combined with a very well-conducted statistical analysis that demonstrates the scope of error that affects your association, right? Usually that's a 95% confidence interval, or it's a p-value, and they basically give you a representation of how much random error goes into that association estimate that we just presented. And that is pretty much standard in every paper we see. That's the random error part. There is also systematic error or bias that we have to deal with when we conduct this research. Usually, when we do research for systematic error, we also do several design-based or analysis-based approaches. These can be things such as matching your groups with and without exposure. You might be interested in stratification. You might be interested in propensity score techniques or some other multivariable methods, or maybe you just want to do some simple regression, multivariable regression models where you account for the confounders or other variables that are important to your study. These techniques are all great. These are all things that are absolutely essential, but they almost never eliminate bias, right? Our goal for none of these techniques was to eliminate bias in the first place. The goal for those processes was to minimize bias, and they're usually pretty good at that. For example, you might have, let's say, confounding in your study, and you might decide that you want to account for all the confounders. Now, you will collect as many confounders as you can. You collect data on as many confounders as you can, and then you will adjust for them in your multivariable regression model. But you may still have unobserved confounders that may be biasing your effect estimate in your study. Another example, you may have misclassification bias, and you may not be able to address that misclassification bias because of the nature of data collection. A good example might be if you ask individuals if they've been using heroin, right? You will misclassify individuals on that variable simply because maybe people don't want to tell a survey researcher whether they've been using heroin. So there is going to be some misclassification bias that you cannot completely account for, no matter what design approaches you take or analysis approaches you take. Similarly, you might have a skewed sample because you don't have a good response rate for your study. And these things all affect your the bias or the systematic error in your results. So what do we do when these things happen? Well, we write up a manuscript, we present our effect estimate with a 95% confidence interval, and we talk about all the great things it does, and then in our limitation section, we say, oh, well, but we didn't have these confounders, and we had a low response rate, and we had misclassification bias, but hey, our results are still great. Right? That is the MO for pretty much every paper. I have written a lot of papers where I've just acknowledged that these limitations exist and then just moved on as if nothing happened. But honestly, we can do better than simply acknowledge that those limitations exist. We can quantitatively account for it. And doing that is quantitative bias analysis. So QBA, the objective of QBA is to quantitatively estimate the systematic error that remains after implementing your study design and analysis. Quantitative bias analysis is not meant to replace the things we do in your study design. It is not meant to replace any of the methods we use in the analysis. It is just meant to help interpret and give you confidence in your results after you do all of those things. Quantitative bias analysis is not super common, but it is not a new technique per se. It has been around for decades now. It's just not popularly used because it does involve a good amount of judgment and a good amount of discretion that the, I guess, a balance that the investigator has to find with their quantitative bias analysis in order to present that confidence in those results. Now, I'm not saying you have to do QBA for every single research study, but there are some cases where this is a really, really good idea to follow. And here are some examples for when that is. Number one, when your study produces a really precise estimate of association with a narrow confidence interval. If your study does not produce a narrow confidence interval and your confidence interval is super wide, you should not consider QBA because you have too much random error going on to tackle systematic error. First, make sure your random error is accounted for with a narrow confidence interval, whether that means you change your analysis, increase your sample size, or whatever else you want to do. Make sure you get an estimate of association with a narrow confidence interval first before you consider QBA. Next, if you have a study where you've got too many biases affecting your results, and there are just things that you cannot account for in your design or analysis, don't look to QBA for help. QBA cannot help you when there are too many threats to systematic validity going on. If you've got a couple of errors here and there that you are afraid might be biasing your results, QBA can help. But be careful because you need to make assumptions when you do quantitative bias analysis as well. And then if you go too far down that road, the results may be meaningless. And finally, QBA is particularly recommended when you are making a policy recommendation. So for example, if you want to say that we should have a mask mandate, or we should mandate vaccines, or you want to make a policy recommendation based on the results you find, you better have a QBA in order to demonstrate that the associations or the evidence you're presenting is actually robust and that there are no systematic biases or other errors affecting your results. Similarly, another interesting case where QBA is great is when you have a very large effect size. So for example, if you find that the association between smokers and having lung cancer has an odds ratio of like 26, right? Like huge odds ratio. Maybe you still have a narrow confidence interval, but a huge odds ratio. A great way to show that that odds ratio is not a result of some statistical quirk or some other error that is going on with your data is to conduct a quantitative bias analysis and demonstrate that that odds ratio is large despite potential existing systematic threats to validity. One thing to remember is that if you are going to do quantitative bias analysis, please make sure you plan ahead of time. when you formulate your study design, when you think about what you want to do for the project, you need to consider what threats to validity exist and then plan for how you're going to account for that. So I'm going to briefly go over threats to validity. And this is primarily intended to be very introductory. So most of you may have had this in one class or another. If you have not, this is going to be a very brief introduction, and then we'll jump straight into how to account for these threats using quantitative bias analysis. The first one is selection bias. Selection bias happens when there are individuals that refuse to participate in your study. And those non-participants are different from the participants in a way that affects your results. This is very, very common today. In today's online survey research world, it is very common to see response rates of 20%, 15%, maybe even lower, right? Especially with those online surveys. Whether or not you provide incentives, response rates tend to be low. When your non-participants or non-responders have proportions of exposure or outcome that are different from your participants, then you will likely have what is called selection bias that you have to account for. The only way to avoid selection bias in a simple survey research study is to make sure you have a 100% participation rate, meaning everybody you invite for the survey actually fills out the survey, or you know the proportions of exposure and outcome, not just in the people that responded to your survey, but also in the people that did not respond to your survey. That's just I mean, both of those scenarios are very, very unlikely, right? How likely are you to get a 100% response rate? Or how likely are you to know all of these distributions in people that did not respond to the survey? Almost never happens. So that's why we need QBA in some cases of selection bias. Similarly, unmeasured confounding. A confounder is a third variable effect which basically biases the relationship between your exposure and your outcome because it is associated with both the exposure and the outcome. Confounding is present in pretty much every socio-behavioral research study we carry out, right? One way or the other. When we have confounding, we usually do a good job of trying to think of them ahead of time, plan for it, calculate data for that variable, and then account it for in our analysis. But it is not always easy to collect that data. Sometimes these are just variables that you cannot ask individuals or you cannot get reliable data on. Sometimes you may be using secondary data sources where the variables that you need to adjust for are just not available in the data set. So you end up having unmeasured confounding. Sometimes unmeasured confounding may happen because you just didn't think about what variables you needed before you sent out the survey. Or maybe you sent out the manuscript to review, and then a reviewer points out that, hey, what if your analysis is confounded by this other variable that you had never thought of before? So when that happens, quantitative bias analysis can be a good solution. This quantitative bias analysis in the case of confounders is particularly helpful if you do have the values of the confounding variable in some subgroups of your study population, but not in everybody for whatever reason. Let's not go into why that might be, but if that does happen in your study, QBA can be particularly an effective approach, though it can work even if that is not the case. Next up, information bias. Information bias happens when the variable that you are measuring is not measured accurately. Measuring a variable accurately, operationalizing it is a fundamental part of every research study, but there are always challenges with accurate measurement. Sometimes the variables you're measuring don't have an accurate gold standard available even for you to compare if your measurements are actually accurate and if they are valid. Sometimes you know that they are not valid and you know that they are misclassified just because of the nature of the data or the nature of the variable. A good example of that might be all of those claims data studies. When you identify something as simple as patients with diabetes in a claims data set, you know you're not measuring that with 100% accuracy. You're missing some people or you're flagging some people that don't have diabetes as having diabetes, right? That misclassification exists in most of the studies we do. When misclassification does exist like that, misclassification bias may happen that can also systematically affect your results, and quantitative bias analysis is one way to account for that. All right, so let's talk about correcting for selection bias. I'm going to stop here briefly to see if somebody has questions before I go into this section of the presentation. All right, so hopefully that was an introduction for most of you. If you have not heard any of that before, that's okay. Please stop by and ask me questions later if you need to. We are going to go into correction for selection bias now. And I'm going to try and take this a little bit slower, and then we're going to jump into a worksheet to see some more analysis for how we can do this. When correcting selection bias, it is important to identify that you have selection bias as early as possible. Conducting quantitative bias analysis to correct for selection bias when you have not identified that earlier is actually much less accurate and much less effective than if you had identified it ahead of time. So if you know that you're going to have low response rates for your study, or if you know that your study population is going to be different from the actual source population for whatever reason, predicting that ahead of time and then planning for it will help you do a better quantitative bias analysis than if you did not. Conducting quantitative bias analysis to account for selection bias is explained as, and I like this quote from the textbook that I pulled, it is asking whether reasonable estimates of participation proportions could account for all of an observed association. So if you have an observed association and you want to talk about how meaningful it is, you need to ask yourself, using quantitative bias analysis, whether estimates of participation proportions or response rates could actually account for all of that association. And if it can, then maybe you truly don't have an association to talk about, right? Another way to phrase that same thing is quantitative bias analysis is asking whether the participation proportion required to counter an observed association are reasonable. So you identify what is the participation proportion you need to basically nullify the observation, the association that you found. And then you ask yourself, is that participation proportion a reasonable guess to make based on what I know about the subject area, this population, and the study topic? And if it is reasonable, maybe you don't have an association. In order to conduct quantitative bias analysis to account for selection bias, you need certain data or parameters. These data can be collected in two ways: an internal validation study or an external validation study. If you were doing an internal validation study, this is usually called a validation sub-study, which is conducted in a small group of your study population. And the goal of this is to basically send a follow-up survey to the individuals that did not respond to your survey and ask them, hey, I know you did not respond to my original survey, but can you answer 2 questions for me? And you're not going to get most of them, but maybe you will get some of them to respond because they are more willing to answer 2 questions than your original 20-question survey, right? And those 2 questions you ask should ask about the prevalence of the exposure and the outcome, because those are the most important things you need to identify. You could also do an external validation study where instead of going to the non-responders from your original mailing list, you simply reach out to the source population separately and then identify the prevalence of the exposure and the outcome in the source population in general, and then use that to determine if that prevalence is different in your study population compared to the source population. And of course, there's always going to be situations where neither option is available. And when that happens, you can still do quantitative bias analysis by simply making educated guesses about these numbers. And interestingly, the textbook takes a very interesting perspective on this. They say that if you don't have these data, don't be afraid to make educated guesses, because it's better than not accounting for these bias at all. Because most studies you look at will simply say, hey, we had selection bias. We know that we had a bunch of non-responders and we have no idea how they may be biasing our study. And the next survey should try and aim for a higher response rate. The next study will never do that either, right? So instead of just saying those things, if you don't have that data, try to conduct a quantitative bias analysis with your best estimates for what you can show. And if you can do that and be transparent with your guesses, then you are still communicating meaningful information that can add confidence in your results. So to talk about how to correct for selection bias, let us walk through this example. This is a study from Stang 2009. Stang and colleagues originally, and this original study was published in 2001. They did a follow-up in 2006. This was a study aimed to identify the relationship between mobile phone use and risk of uveal tract melanoma. I think that's how you say it. I've never had to use that word in a presentation before. In fact, I had to look it up to make sure I knew what an uveal tract was. But they were looking at the relationship between a mobile phone use and risk of uveal tract melanoma. Their original study was actually much more expansive. They were looking at all forms of radiation exposure and the melanoma incidence. But this sub-study, which is where we are looking at the selection bias QBA, focuses on mobile phone use. And if you're wondering, isn't 100% of your population going to be using mobile phones? They had an older data set where they collected individuals between 1997 and 2001, I believe, were the original years for the data collection. So there was some variability in whether people use mobile phones or not. Anyway, this study was conducted using a case control design. John, if you're laughing, that was my first question. When I read this, I said, wasn't 100% of your study population using mobile phones? And then you can't do any analysis, but it was an older data set.
That's good.
All right, so let me walk you guys through how they did this study. So they used a case control design. They had cases that they identified at a tertiary hospital in Germany, which is where the study was conducted. And they had 486 cases of uveal tract melanoma identified in this 3 to 4 year period when they were recruiting individuals. They approached all 486 individuals and asked them to participate in an interview. 485 said they would participate. And out of that, 30% used their regular mobile phones regularly, and 23% did not use their mobile phones at all. And the rest of them had some varying degree of intermittent mobile phone use, but they did not want to include them in the study, so they excluded that middle group. Similarly, they identified 1,527 eligible controls without uveal tract melanoma that they had identified from the population at large. So this group was identified from the hospital. That is a population-based control. In fact, in the original study, they also had a hospital-based control, but we are not going to talk about that now because this QBA is specific to the population-based controls. Well, when they reached out to the general population, of the 1,527 study invites they sent, only 840 agreed to do an interview, of which 35% were involved in the regular mobile phone use, and 20% said they did not use mobile phones. Anyway, the odds ratio, when you look at this study and these numbers, was found to be 0.71, which is the number you get when you do a cross-product ratio. For anybody that's been in my pharmacoepi class, hopefully, you remember how to do a cross-product ratio, but we will also show that on the screen in just a second. So if you've not been in my class, that's okay. But let's talk about the non-participating individuals, right? So in this numbers here, between 483 and 485, typo there. There's a few people that did not participate. There's actually 27 people that did not participate. I think that number was 497. Excuse me. I think I had a typo there. That is 497 eligible incident cases. But those 27 non-participating cases were sent a follow-up survey that said, hey, I know you said you don't want to participate in a 2-hour interview. That was a larger, much more expansive study. But can you answer these short few questions for us? And of those 27 people with uveal tract melanoma, 10 of them responded, of which 30% said they use mobile phones, 70% said they do not. And similarly, of the 663 non-participating population-based controls, 284 individuals, 43%, responded to the same questionnaire, indicated that 25% of them use mobile phones, 75% did not use mobile phones. Interestingly here, observe this, the response rates, the participation rates in the cases was 94% in the original study, 55% among the controls. So there's already a big disparity in participation rates between cases and controls, and that should get your alarm bells going to say, hey, maybe I have potential selection bias. But once you look at this data, which is from that short questionnaire that came after the original study, you know that there was selection bias because if you calculate that same odds ratio showing the relationship between mobile phone use and uveal tract melanoma, but among these non-participating individuals alone, you find that the cross-product ratio gives you an odds ratio of 1.25, whereas the original study odds ratio was 0.71, completely in the opposite direction. So you know there was selection bias because the non-participants have an association between these two variables that is different from your study population. All right. So how do you account for something like this? Actually, before I talk about how do you account for it, this is the cross-product ratio I was mentioning. I just want to show this in table form. So for those of you that have not taken how to do analysis of case control studies, you simply draw a 2x2 table with your cases, people with uveal tract melanoma, controls people without uveal tract melanoma, regular mobile phone use, no use. You write your numbers down and you simply do a cross-product ratio. 136 multiplied by 165 divided by 107 multiplied by 297, that is 0.71 right there. And in your non-participants, we simply did the same cross product ratio, 3 multiplied by 212 divided by 72 multiplied by 7. And we got an odds ratio of 1.25. Obviously, very different odds ratios indicating that we have selection bias going on. So here's how we try and address this problem. Now, we do know that there were 17 cases and 379 controls for whom we do not know exposure status. Who are these people? So these are the 17 people that did not answer to this short questionnaire and the 379 people that did not answer the short questionnaire. These are individuals that did not participate in the main interview study and they did not respond to the short questionnaire, right? So we don't know the probability of exposures or outcomes in those people. But maybe we can make some assumptions. Maybe we can assume that in those people, the distribution of mobile phone use was similar to these 10 people that participated. So I know 17 people did not respond here, but maybe their distribution of mobile phone use was similar to these 10 people. Now, you could also argue that maybe those 17 people were similar to this original 485 instead of this 10. And that would be a great argument. And if you said that, I would say, great, we can do 2 quantitative bias analyses and look at different variations and see how results change. But for now, let's make the assumption that the people that did not respond even to the short questionnaire were actually similar to the people that did respond to the short questionnaire. Okay? So if you make that assumption, these 17 people that did not respond to the short questionnaire had 30% mobile phone use, 70% no mobile phone use, and the 379 people, 379 controls that did not respond to the short questionnaire had 25% mobile phone use, 75% no mobile phone use. And that brings us to recalculating our numbers, which would look like this. So now what I'm doing is I'm taking that 2 by 2 table that, that this 2 by 2 table to the left right here. I want to take the same table. I want to add the numbers of the non-participants. So this 3 gets added to the 136, the 7 to the 107, the 72 to the 200, because we know the distribution of these variables in this group. So we can just add them to the original group, and the other 17 and 379 people, we make assumptions about them or about their distributions of mobile phone use and add those as well. And this is what that would look like. So the 136, which was the original study population, the 3 individuals, which was the non-participants that responded to a short questionnaire, and then the 17 individuals that did not respond to the short questionnaire multiplied by 30%. Right? You saw where I got that 30%. And then we do the same for the no use. 70% of that 17 was added to the 107 and 7. Similarly, we did the same thing with the controls. 279 people was the original study population. 72 was the people that responded to the short questionnaire. And then 25% of 379 was the number of people that did not respond to either the interview or the short question. And we did the same thing with the no use. Got total numbers by just adding those up. And then did the same cross product ratio, 144.1 multiplied by 661.25 divided by 125.9 divided by 463.75. And the odds ratio is 1.62. Very different from both of the odds ratios we originally got. But this is the adjusted odds ratio after conducting quantitative bias analysis. Very simple, right? I didn't do any complicated math. There's no complicated analysis here. This is called simple bias analysis. And you can see that if you want to make it more complicated and add more layers to it, there is options to do so. If you want to get those same numbers, but you don't want to actually do the math like we just did, you can get those numbers for the adjusted odds ratio by using the simple formula, where you take the unadjusted or the observed odds ratio from your main study and multiply it by the selection proportions. And then you will still get your adjusted odds ratio without having to do all this math and addition that I just did.
Is that also, could that odds ratio be a multivariable adjusted odds ratio too? So this would be an easier way to do it if you've already got adjusted for potential confounding.
So that is a really good question. I'm going to say yes, but there are some caveats to that, as you might expect. I can get back to that later if that's okay. But that is a really good question. So the selection proportions presented here correspond to this table. So S case 1 is the proportion of respondents among people with uveal tract melanoma that had regular mobile phone use, and so on and so forth for all the other 4 numbers. If I were to do this using that formula instead of the math that we just did, the selection probabilities would look like this. I just divided 136 divided by 144.1, which is the total. So 136 was the original number of responders. 144.1 was the total after doing that addition. And that is a 94% selection probability in that first cell. Selection probability here was 85% because I simply took 107 number of original responders for the study divided by 125.9, which is the total after I did that math. I got 85%. And when I do that math, I get 1.61, which is slightly different from the other one because of rounding errors. It's basically the same number. We just have some rounding issues going on. So with that, let me jump to a worksheet to show you how to do this without having to do any math at all. So these worksheets were actually provided with the textbook. They're also freely available if you want. And I've been trying to upload them on Blackboard. I think Blackboard doesn't like these macro-enabled worksheets for whatever reason. But I will upload them to Box, post a link in Blackboard so you guys can still access them. So this is the same study we just looked at, right? We are looking at the relationship between uveal tract melanoma and mobile phone use. And the way this worksheet works is actually very simple. You enter the numbers you want in all the blue cells, and all the answers are represented in the green cells that are at the bottom. You'll see when I scroll. So these numbers, 136, 297, is that big enough for the people in the back to see?
You're good.
No, it's okay. I know we're also recording, so I'm going to zoom in. Okay, so these numbers, 136, 297, 107, 165, are the same numbers I just showed on the slide a second ago. So you have to enter these 4 numbers in, and then you have to enter in the selection probabilities within each group. So the selection probability for the people with uveal melanoma that were mobile phone use was 94%, if you remember from our table on that last slide. And then 85, 64, 25, all numbers from there. You enter mobile and UM here just to help with the labeling on this 2x2 table because it's easier to understand with the labeling. And if you just skip everything and go right here, there's your selection bias adjusted odds ratio. Again, some rounding issues going on, but that's the same number that we got from the earlier 2 slides. Right? And this worksheet does all of that math on the back end. And if you want to understand how this works a little bit more, you'll see here that these adjusted for selection proportions are the same numbers that we got after we added up and made assumptions about what those non-participants look like, right? So 144.7, 125.9, same numbers, they are just showing us their math so we know how they are working. The other interesting thing to see in this worksheet is the selection odds ratio. This selection odds ratio is actually this right here. Or in other words, it's this. It's the selections for these 2 multiplied by these 2. That is what they're calling the selection odds ratio. So you get that number by simply doing this math. And that is 0.43. It's actually the inverse of 0.43, but you just have to divide it by that to get that number. So this worksheet can simplify the process of basically going from case control data where you know you've got selection biases to potentially accounting for them by conducting the quantitative bias analysis. I know we're running out of time, so I'm going to try and move back quickly, but please interrupt me if somebody's got questions. All right, so let's briefly touch unmeasured confounding because it's probably the one most of you guys will try to use. I won't show how this formula was derived or how the simple math behind it works, but this is not super complicated to understand either. Just pick up the textbook. It's very simple to understand, and the book does a really good job of dumbing this down to a point where it looks really simple. In order to correct for unmeasured confounding using QBA, you need to have 3 parameters. The first one is the association of the hypothesized confounder and the outcome among individuals who were not exposed in your study. We are calling that the risk ratio CD. and then CDB meaning relationship between confounder and disease. And then you also need the prevalence of confounder among those with the exposure of interest and the prevalence of confounder among those without the exposure of interest. When you know those three things, you can simply plug it into this formula, and the observed risk ratio can be converted to an adjusted risk ratio using this formula. And there's also a worksheet that can help you do this if you don't want to do that math yourself. Now, where do you get these three parameters? Now, ideally, if you had a confounding variable that was measured in a small subset of your study, maybe you are using a data set like MEPS to do your analysis, but that important confounder was present in a additional supplemental questionnaire that was administered to 30% of the patient. You could use that data to do this. Or perhaps you were using a data set which had a lot of missing variables. So you've got this other variable, but it's not reliably measured except for in like 10% of the population. You could still use this. And let's say none of those things exist. As a researcher, you can still do a literature review to identify the relationship between the confounder and the outcome among the individuals without the disease, and identify the prevalence of exposure, prevalence of the confounder with and without the exposure, just from published literature, and then plug those into the formula to see if you can adjust for quantitative bias analysis. Now, when using literature values, it is ideal to not just use one number, but to do what is called multi-dimensional bias analysis, where you look at a potential range of numbers to see at what particular value range your association will basically go away. But that is just recommended practice. You could simply plug in one number and you get a meaningful estimate, even if it is not perfect. All right, so I'm going to stop there. We are not going to talk about misclassification bias and correcting for misclassification bias, just because we are running out of time. But know that adjusting for misclassification bias is also just as simple. All you would need is the sensitivity and specificity for the measurements for both your exposure and your outcome. When you have those four numbers, you can plug it into a formula or use a worksheet to get a similar bias adjusted estimate of association for misclassification. But often the challenging thing with QBA is not doing what we just showed. What I just showed is the really easy part. The more difficult part is putting together an analytic plan for how you're going to do your QBA, what numbers you're going to use, how you're going to justify it to your reviewers, and gain confidence in your study results. And this is particularly challenging because most studies have more than one type of bias. My limitation section in any manuscript I've ever published has never been one sentence long. It's just never been one. It's always been a paragraph or two paragraphs long, right? Because that's just the nature of the studies we do. We have a lot of limitations. When you have multiple limitations, it is not appropriate to just do all of these quantitative bias analyses one after the other. You can do them one after the other, but the order of adjustment becomes very important. And it is because the adjustments that we do with QBA are often not multiplicative terms, not simply multiplicative terms. If they were all simple multiplicative adjustments, you could simply chain them any way you want and assume that the biases are not building on top of each other. If you make that assumption, this would be acceptable. But particularly the adjustment for misclassification bias is not a simple multiplicative adjustment. There is more change that is involved in that adjustment. So you have to be careful with the order of bias adjustments you do. This rule of thumb to follow when you have to correct for multiple types of biases is that you should correct them in the reverse of the order in which they arise. Okay, this is what that generally looks like. The first bias you should correct for is the bias that happens in your study population. Right? The study population you have may have information or misclassification bias because the variables you're measuring are not perfectly measured. So correct for that one first. Next, you may have selection bias because your study population is not comparable to the source population due to low response rates. That is the second type of bias you should account for. And then finally, you may have confounding, which is a type of bias that affects the whole source population, not just your study population. And that is the last type of bias you should account for. So you should address them in the reverse of the order in which they arise, starting from where your study was conducted all the way back to the source population. Now, this is a general rule of thumb, and there are going to be exceptions depending on the order in which your data were collected. For example, if you calculated data for misclassification bias, but you did it before all the individuals responded to your study. So the initial screener email, which saw if individuals were eligible or not, if you added questions to that to do your misclassification bias, then you would need to flip these two because you calculated that data before you have potential selection bias. So essentially what I'm saying is think about the process in which data were collected for your study and reverse the order in which these biases occur when you are adjusting them. All right. I think I've got time to show one more thing. Probabilistic bias analysis. I briefly mentioned multidimensional bias analysis, but I skipped it because I think we'll talk more about this in a second. But I'm happy to go into that later as well. So probabilistic bias analysis, or PBA, is the more common bias analysis you will see. When bias analysis is published in the literature, the most commonly accepted form that reviewers won't harass you over is PBA, not what we did earlier, which is called simple bias analysis. With simple bias analysis, you were taking one value of a parameter, right? You were saying, hey, I think this is the exact number of selection proportions that we have, and I'm going to plug it into this formula, and I have this one magical number. That almost never flies in a manuscript. What you need to do is called probabilistic bias analysis, where instead of assuming that those parameters take one number, you assign some probability distributions to those parameters. So you don't say the selection proportion was 94% in this cell. You instead say that selection proportion is a normal distribution with a mean of so-and-so and a standard deviation of so-and-so. Or you say it is a uniform distribution with a minimum of this and a maximum of this. The authors of this textbook particularly like a trapezoid distribution, where you basically go like that, where you have two modes that bound the upper and lower end of that parameter, where the parameter is most likely to lie. But just to cover your bases, you add two additional, a min and a max, on top of those two modes, so that you check not just the likelihood that the selection proportion or whatever parameter you're selecting lies between those two modes, but also a potential outlier, if you will, to see if those affect your results. The advantage of doing a probability distribution is you're not held to one value now. You can use Monte Carlo estimation to repeatedly do 5,000, 10,000 random draws of parameter estimates from this probability distribution I was assigned, and then use them every single time to correct your estimate of association and present a whole range of adjusted association estimates. Right? So you don't just have one number. After adjustment, you've got a whole frequency distribution of numbers. That is usually much more powerful than doing bias analysis. In fact, when you have that whole frequency distribution, one thing you can do that makes it very easy to interpret and understand to most of us who are used to seeing things like confidence intervals is to present what your textbook calls the systematic error simulation interval. They sometimes abbreviate it as simulation interval, or they call it uncertainty level, and it is calculated like this. So you take the range of adjusted estimates you get from doing a probabilistic bias analysis, you identify the median, the 2.5th percentile, the 97.5th percentile, and then you label those two numbers as the limits of your 95%, not confidence interval, but simulation interval. You cannot quite call it a confidence interval because you can't interpret them the same way, and because they're not based on the frequentist school of thought at all. In fact, the textbook authors argue that this is borrowing from a Bayesian school of analysis because you have a prior known distribution of that bias parameter, that selection or non-response parameter. You have a prior known distribution, and you use that to adjust the risk ratio you found. So if anything, it borrows from the Bayesian school of thought, not the frequentist school of thought at all. Anyway, you get that 2.5th percentile, 97.5th percentile, and now you can say that that range indicates the limits between which 95% of correct estimates lie. Right? And once you've done that, you can then present results that look like this, which I really like this table and the next table I'm going to show you in a second. So we usually see this first row in all of our analyses, correct? You present the conventional analysis results as the point estimate and a 95% confidence interval. So they recommend showing that, and then an additional row of data where you show the systematic error adjusted estimates that were calculated using probabilistic bias analysis, and they present numbers that look similar to those. So everybody knows how to interpret them without struggling too much. And you also clarify how that affects implications for your study. The one next thing I want to clarify is you don't just have to stop here. You can take it one step further, right? So up to this point, what we've talked about is we already know the random error part. We've talked about adjusting for quantitative bias analysis and then doing it using probability distributions and then producing an interval, a simulation interval that accounts for or explains the effect of the systematic bias on your study. There is a way to now combine these two. So you can now produce estimates that account both for the random error in your study and the systematic error in your study. So in order to do that, the authors recommend a very simple approach. Take the systematic error point estimate, the 0.92 from the second row here, and simply multiply it by a random standard normal deviate between 0 and 1, multiplied by the standard error of the estimate from your conventional analysis, and then you will obtain a total error analysis. The formula behind it is very simple. If you don't want to work it, there is a worksheet that I can introduce you to that does the same thing, and I think we have time for me to show you that. But essentially, all it does is it combines the estimates of error, the standard error from the random error and the point estimates from the systematic error, and produces this total error that basically combines both pieces of information and presents us as one simple estimate that we can all interpret and understand. Just be careful that you don't call that 95% interval a confidence interval, because it's not a confidence interval at that point. The other thing, I have one more example. The other thing I want to mention is that these worksheets are freely available, but if you don't want to use worksheets, or if you have more complicated analyses, like what John was suggesting earlier, there are actually SAS macros and programs that can do this for you. And they're available for download on the Brigham and Women's Hospital Pharmacoepidemiology website. Now, the one thing I will say is we've been talking so far about using summary data to do your quantitative bias analysis. Meaning we did with the selection bias example, we looked at 2x2 tables instead of looking at individual level data. Right? We looked at summary data, and it is possible to do QBA with summary data and have it be done robustly, right? Absolutely is possible. But there are also approaches to do it at record level data or individual level data in a way that is more robust, if you will. But it obviously involves a little more sophistication and a little more advanced planning and programming, if you will. There are no simple worksheets to help you do that, to do that math, but that has been done before. The other thing that makes this interesting is whether you use adjusted estimates or unadjusted estimates when you do your quantitative bias analysis. This was John's question earlier, which I think is a really good question, because that was the first question that comes to my mind as well, right? If I need to do this for my study, I will say that I have seen both in the literature. So some of these examples I presented earlier were actually unadjusted estimates. So they just take they trust the study design to say, I've identified an estimate of association with a narrow risk of with a narrow confidence interval because I've got a robust study design, and I'm going to take an unadjusted estimate and then use quantitative bias analysis. But I think it is also possible to use an adjusted estimate. The difficulty with an adjusted estimate is you may not have the summary tables if you want to do the math yourself. So you have to rely on the formulas to do them for you, which is still doable. And I think it can be published even like that, because I've seen those papers. I just think they're a little murkier to interpret because you don't see the math that goes into the unadjusted association directly, because usually it's an output from a multivariable model, right? Having said that, let me quickly jump into the other worksheet I want to show you guys today. I think I'm doing okay on time. All right, so this is the same example we talked about just now, the relationship between uveal tract melanoma and mobile phone use, but instead of assigning, these selection parameters, 94%, 85%, 64, and 25%, which we obtained those because we had data for that study, which allowed us to make those assumptions. But if you did not have that, you could simply use this worksheet, which assumes a trapezoid distribution where you guess what those parameters might be. So I inputted these numbers while I was preparing for this presentation, and I said that study tells me that the selection parameter estimate for that group is about 95%. I'm going to say the modes are 90 to 95% with a min of 80% and a max of 99%. Right? And then I just randomly pick numbers. Now, if I knew any more about mobile phone use or uveal drag melanoma, I would have made more educated guesses in this worksheet. But for now, these are just numbers I picked out of thin air. And you can choose how many you want to run. This takes time if you do too many, so I'm going to do 150. And then you enter the same proportions that we talked about on the original spreadsheet. And when you hit run simulation, when you run simulation, you see on the right here, it actually starts generating all those numbers. So it does the calculations up here. And it very neatly actually presents the numbers chosen from the probability distributions for those 150 random draws. This is what those numbers look like. And these are the results for the simulation. So let's look at the odds ratio simulation, because we've been talking about odds ratio so far. If you remember, the conventional odds ratio was 0.71. The systematic one, after doing the probabilistic bias analysis and including the simulation interval, was 1.24 with a range from 0.64 to 2.94. And the total error, which accounts for both the conventional or random error and the systematic error, is 1.17 with a confidence interval. See, I caught myself saying that. With a simulation interval between 0.58 and 3.17. But what this shows is that the original study did show an association between mobile phone use and uveal drag melanoma, but maybe that association was biased because we had selection bias affecting our study results. Of course, you can't really trust these. I pull these numbers out of thin air. But if you were to do this right, you would be able to make such inferences and potentially add confidence to your study results. I've got one more example in the slides here. I'm going to skip this and allow time for questions. If we have time, I'll come back to them. But I will say that this study published by Bodnar in 2006 presented results that look like this. And I thought this was a really neat way to present those results. They've got adjusted odds ratio from a conventional analysis, a point estimate from the probabilistic bias analysis, and the total estimate, that is both systematic and random error, in that last row of data. And they did it separately for the total population for individuals with that were not obese and individuals that were obese, I think was the groups that they identified. And their study actually added confidence to their original findings. They were looking at associations between multivitamin use and risk of preeclampsia, and they found that multivitamin use does protect you from preeclampsia during pregnancy. And the quantitative bias analysis they did reinforced the fact that their findings were actually accurate. The challenge with presenting QBA is how to present and how to interpret your results. Wherever possible, be transparent, not just with the fact that maybe you chose to do your QBA after your original study was conducted, but also with what methods you used, if you used a worksheet, what input parameters you used, and how you got those input parameters. If you just took random guesses, be honest and transparent when you talk about it. It also helps because I think in most journals, reviewers may not be aware of QBA to actually talk about the math that goes behind adjusting those odds ratios and risk ratios. Now that part is not actually as complicated as it sounds. You can walk through a simple example or a simple adjustment like I did here with the formula, and then mention that you did a probabilistic bias analysis that drew random numbers and did it several thousand times to get an estimate and an interval. But walking your reviewer through that math and your reader, if you are publishing a journal article, is going to be super helpful to help the reviewer understand and the reader understand what you are doing. The other thing to remember is it is very, very easy when you do probabilistic bias analysis to have so many results that you don't have a succinct way of presenting them. Just because you may have tables upon tables upon tables of data. You might want to run probabilistic bias analysis with one set of numbers, another set of numbers, and then you want to run, after correcting for selection bias, maybe you want to correct for confounding, and then maybe you want to correct for something else. You might end up with tables upon tables upon tables of data that are difficult to interpret and difficult to present. So be careful with the decisions you make when you plan to do this. And wherever possible, present your results using figures instead of actual numbers. So the probabilistic bias analysis intervals that we saw, those simulation intervals, instead of presenting them like numbers, present a histogram. Right? Present a histogram that shows here is the range of adjusted association estimates I found, and that can help you interpret whether there is an association or not. Or better yet, if you've got multiple types of biases you're accounting for, do a tornado diagram. Like those ones you see in a meta-analysis, right? Those can also be very easy to interpret and understand. And if you've got to stick those tables somewhere, stick them in an appendix or a supplement, right? Here are the resources I want to recommend. I'm going to wrap up with this one. That textbook is the one where I got most of my information from today. It is a really simple, easy to read and a short, brief textbook. I would strongly recommend buying it. If you don't want to pay for a textbook, this first article, the good practices for QBA, is a really, really good read. It's the same content as the textbook, actually. It was published after the textbook came out. It does not include all the formulas we just went over, but it essentially talks you through what it is, how to do it, how to plan for it, how to collect data. It's a really good read. If you are conducting a study or planning one, maybe you're writing a research proposal and you want to know how to write for QBA in your proposal, look at this article. Again, a really good read. And these are the two examples we just went over. I'm going to stop there and just see if anybody's got questions. That's probably the most fun slide I've had all day.
So thank you for the presentation. This was really informative. One question that I had, going back to the unadjusted analysis when we're doing the probabilistic bias analysis. Is there a way, is there any guidance if we want to select a distribution other than the trapezoid distribution, is there any guidance of how?
So there is a SAS macro that lets you do probabilistic bias analysis for selection bias, and I believe there is one for misclassification. I have not seen one for confounding.
Okay.
And they let you choose any distribution you want. The textbook actually includes a little bit of VBA code, Visual Basic code, to incorporate within Excel if you want to use a different distribution.
Right. Another question I had, probably again, we may not have, I mean, I am not aware of this, so I was curious. If we are running a probabilistic bias analysis on adjusted estimates, so we have covariates in the model, will the distribution of my bias parameter be affected by the distribution of my covariates?
That is a really good question. One way that the textbook explains that is they say that, for example, if you're talking about confounding, you have to make sure that the association that you are adjusting is, if it is going to be unadjusted, you have to make sure it is not confounded anymore. Now, if you know that the unadjusted association between exposure and outcome is actually confounded by a third variable, even the simple Excel worksheet for unmeasured confounding has options where so it offers multiple scales, but it also offers uncontrolled confounding with effect modification or without effect modification. In fact, you can even go further and say, what if some of the variables have a correlation, and that affects your study results. And you can also account for that with the polychoric tab. So you've got all of those options, particularly in the confounding one, but not so much in the other ones. So yeah, those are definitely things to consider when you're doing this analysis.
I have more questions, but I see how it is.
Thank you. Anybody else?
Is there a preference for individual records or summary? The one you were saying that we can do either individual or summary. So
In terms of sophistication, the summary data are so much easier to use. And
Where
you
do
can
you
pick up
prefer-
that worksheet.
what do you prefer, one over the other?
So that is a good question. You can stick with the summary data, with the worksheets and the formulas I showed, and keep it simple as far as possible. The only exceptions to that rule are if you know that you've got several types of bias. So you are accounting for 2 or 3 types of bias in the same study. And if you use summary data at that point, you may be making too many inferences. The other thing that record level or individual level data gives you is it lets you study relationships between the adjusted estimates and the other variables in your study in a way that the summary data don't directly let you do so. So when using summary data, it may be preferable to simply use unadjusted associations as long as you have no reason to believe there is significant confounding going on. But if you can do record level data, it is definitely superior. Good question. Thank you. Anyone else? Did you have something else?
Yeah, I just wanted to pick your thoughts on how you would approach it. So QBA is great, right? But there is also a lot of work and consideration that has to go into it. So let's say I am working on a study and the effects that I have gotten, they are precise. So they are primary candidates for a QBA, and the effects are also large. So that's another primary candidate for a QBA.
Yeah.
But the relationship that I'm examining, my observed study effects, they are consistent with what is seen across studies. So in that case, are there any efficiency gains in doing a QBA? Would you say a QBA is necessary? If,
you are going beyond my knowledge here. My intuition is to say it depends on your study, right? If it is consistent, but you know that there are biases, then I think you should do QBA anyway.
Okay.
But if you are comfortable and if the findings are supported by theory and you're not worried about how much bias is affecting your results, maybe you don't need to. But again, this is where you got me out of. I've never done a study with a quantitative bias analysis either. This was my summer reading, and I'm happy to share with you all. But I acknowledge my lack of experience with this analysis here. Those are good things that I would love to explore one day.
Me too.
All right, anybody else? If not,
Quickly about the idea of the educated guess. I mean, this example is a pretty easy exposure outcome, right? Like I'm going to know if I have cancer, I'm going to know if I have used a mobile phone, and that isn't extremely burdensome to ask. So your ability to get your non-responders to respond to that might be good. But we don't always work in areas like that. So we're going to have to use that educated guess option. What a reviewer is going to ask about when I say, well, I took an educated guess, right? Like, are you using prior literature? Are you using, what are you using?
so one way that I've tried to explore, and I've been trying to read more about this as well, is when you take an educated guess, always, of course, justify it, back it up with something. But one way to get at those selection proportions is to say the proportion of, I'm going to pick an example from things that I published here. Stimulant misuse in my study was 20%, but I know that in the general proportion, in the general population from all these other studies, the numbers are close to 10%. So then I back my way into what kind of non-response I would have had to get me to 20%, and then use that as my base number to build distributions around, and then do these analyses. So you could justify it with things like that, but one of my favorite applications of QBA is to say, I don't think we have any biases affecting our study, but we may have had unmeasured confounding. And there is one paper that I did not present today that basically said, to what degree of unmeasured confounding should we have had in order to make these results meaningless? And they talk about the prevalence of this imaginary confounder in both study groups, and they talk about the relationship of this imaginary confounder with the outcome and make guesses about it, and then show in order for this imaginary confounder to truly make our results invalid, this is how strong the relationships have to be. And then you look at those numbers and go, if there was such a confounder, I would have known it from theory, I would have caught it in the data, or I would have observed it anywhere else. And because we did not, this is not actually a problem. And so even with completely imaginary variables where you have no numbers to go off of, as long as you're presenting reasonable inferences, I think you can do this. The challenge again is the judgment that you have to make, right? Like you have to make an argument that is sound. So this article I was reading basically took this imaginary confounder that had a very skewed distribution between their cases and controls and a very strong association with the outcome, and said, you have to be this skewed and have this strong an association in order for this association to go away. And that is almost impossible. And you can see that any other numbers we've tried where the distribution is not as skewed or the association is not as strong, association is still present and our study results are valid. So if there is such an imaginary confounder, it doesn't affect our results. So those were based on complete guesses with no justifications whatsoever. That was actually one of my favorite analyses. There was just too many things to talk about in a 1 hour presentation. Anything else? Those were good questions. I encourage you all to consider quantitative bias analysis in your upcoming projects, and please reach out if you have any questions. I will try and make all of these Excel files and everything available to you through Blackboard. The slides are already up there, and I'll post a OneDrive link. The SAS macros are also up there. Blackboard wouldn't accept those Excel files for whatever reason. I'll upload them to OneDrive, to Box, and then share a link on Blackboard. Thank you all. Next week, Samal and Wes will be presenting their topics about the impact of code. Thank you.